You probably use microcontrollers every single day, in your phone charger, your car, your headphones, your microwave, even your toothbrush. But unlike a full computer, a microcontroller is designed for one specific job. So how does a tiny chip read sensors, process data, and control the real world all by itself? Let's break it down technically. A microcontroller, or MCU, is essentially a complete computer integrated onto a single chip. It contains three critical components. First, the CPU, which executes instructions. Second, memory, usually flash for program storage and SRAM for temporary data. Third, peripherals, which allow the chip to interact with the outside world. Unlike a desktop CPU, microcontrollers are optimized for deterministic timing, low power consumption, and direct hardware control rather than raw computing performance. At the heart of the microcontroller is the CPU, typically based on architectures like ARM Cortex-M, AVR, or PIS. The CPU operates through the fetch-decode-execute cycle. First, it fetches an instruction from flash memory. Then, it decodes what operation is required. Finally, it executes it using registers and the ALU, the arithmetic logic unit. This happens millions of times per second, driven by a clock oscillator that defines the instruction timing. Because many microcontrollers use Harvard architecture, program memory and data memory are physically separate, allowing faster parallel access. Microcontrollers typically use three memory types. Flash memory stores the firmware permanently, even without power. SRAM holds runtime variables, stack, and buffers. EEPROM, when present, stores small persistent data like calibration values. Memory constraints are usually tight, sometimes just kilobytes, so efficient coding and memory management are critical. Also, interrupts and stack allocation must be carefully controlled to prevent overflow. What makes microcontrollers so powerful is their peripherals. GPIO pins allow digital input and output, turning LEDs on, reading switches, or driving motors. Analog peripherals like ADCs convert sensor voltages into digital values. Timers generate precise delays, PWM signals, or event scheduling. Communication modules, UART, SPI, and I2C, allow connection to displays, sensors, and other chips. These peripherals operate through memory-mapped registers. Writing a value to a register directly configures hardware behavior. That's why embedded programming often feels like controlling hardware at the electrical level. One defining feature of microcontrollers is interrupts. Instead of constantly polling sensors, hardware events can pause the CPU and trigger an interrupt service routine. This enables real-time responsiveness, crucial for motor control, communications, or safety systems. Latency, interrupt priority, and deterministic timing are key design considerations in embedded systems. This is why microcontrollers excel at control tasks, even with modest clock speeds. Microcontrollers also include low-power modes, sleep, deep sleep, and standby, allowing battery-powered devices to run for months or years. Clock gating, voltage scaling, and peripheral shutdown are common techniques used to minimize energy consumption. So in simple terms, a microcontroller is a compact computer designed to interact directly with hardware, sensing inputs, processing data, and controlling outputs in real time. They're small, efficient, specialized, and they quietly run much of the modern world. Thanks for watching, and don't forget to like and subscribe for more tech deep dives.